So I'll talk about the ways in which we are quantifying systolic function traditionally, and also some of the methods that are coming online right now, and then a little bit about what might be available in the next 2 or 3 years. Okay, so I'd like to declare that I am a consultant for Siemens, off and on. There will be a little bit of stuff that I'll talk which was funded by Siemens today, but I'll point that out on the slide. The rest of it is independent. Okay, so we've heard a lot about CMR for image analysis and cardiac quantification. So cardiology is really a quantitative practice. So we want to not only look at the images and qualitatively assess what's going on there. We can get a long way with that, but we also want to actually quantify in terms of indices which are readily understood by the patient and the clinician what the cardiac performance status is. And we've heard about a wealth of data that MRI provides the clinician. So I'm just going to concentrate on right and left ventricle volumes and mass and regional function in terms of regional strain and motion. There are some very good standards or recommendations published. There's a few good ones in the Journal of Cardiovascular and Magnetic Resonance coming out about recommended protocols, recommended ways of acquiring images, and also of the analysis. These slides, I'll try and put them up on the Cardiac Atlas website afterwards as well, so you can download them from there shortly. So the bread and butter for systolic function has been, since the early 2000s, steady state free precession, also known as true FISP by the Siemens people. Buffy, I think, was a name that was around at some point for Philips. Balance FFE, and GE has Fiesta. Right. If anyone wants to earn a prize, they should standardize the nomenclature of the gradient recall echo. There's a plea. Okay, so this pulse sequence is really interesting. It's got a very short TR. It's completely symmetrical in all the gradients, and all the gradients are nulled. So the first moments are always 0 on every TR. And if you do that, you get this weird increase in signal, which is much more than you would expect out of a sequence like this. It's kind of a merge between a spin echo and a gradient echo, where the signal is proportional to the ratio of T2 to T1 plus T2. And that you actually get a lot of signal for a very short time period of imaging. The recommendations from Jeanette's first author paper on this have been around for a while now. So in terms of contouring, the standard contouring method is still getting a pencil kind of and circling all the contours. I'll talk about some of the automated methods next, but I thought it would be really good to start with how to contour a case. And you'd think that we'd known this for many years now, but it turns out that there is still points of contention, as we found out with a study that I'll talk about next. So this is the Society of Cardiovascular Magnetic Resonance recommendations for how to contour the LV. There are two ways you can do it. You can either exclude the papillary muscles and trabeculations from a myocardial mass estimate, or you can include trabeculations and papillary muscles into the myocardial mass estimate. Kind of the jury is a little bit still debating this. It's a controversial area. A lot of packages are now coming up with the option to automatically pick out all these little bits of muscle and add them into the mass. However, I think we still need some large studies to figure out what the reproducibility is of this between centres. A lot of centres do it by rejecting the papillary muscles from the myocardial mass, and the reason for that is that it's more reproducible. So the idea is that from a scan-to-scan reproducibility, the imaging that we get nowadays is still 2D slice based. Each of those slices is quite thick, and often if you rescan a patient, you may not be scanning exactly the same slices as you were before. Other little tricks are contouring the mass of the apex if it appears. That can be very difficult on a short axis scan because of partial voluming, and also up around the base that can be difficult too due to the through plane motion. So you have to figure out what's myocardial and what's atrium as the valve comes through, and also the recommendation is that you include blood up to the leaflets of the aortic valve, and that can be a little bit tricky too because they can be a little bit higher than the myocardium. So recently we decided to do a study which was an interesting study, but we learned a lot from it. So we got 7 very well established cardiac MR core labs to contour the same 15 cases. And this took about a year to actually get everyone to contour the same cases. But eventually we found some interesting things. So we found that the variation, as you might expect, is highest at the apex and base and least in the middle of the ventricle. However, this variation doesn't really add much to the mass or volume calculation. The bit that changes your mass and volume calculation is subtle biases around the contours on every slice. So from our 7 expert readers, we were able to calculate mathematically a maximum likelihood segmentation or maximum likelihood contour for each of these cases, and the results of some of them are shown down here. So these, we call them consensus contours, don't actually reflect any one particular core lab, but are kind of like a merger of 7 core labs who have been doing this for many, many years. And you can get these images and these consensus core labs from the Cardiacatlas website. If you look up cardiacatlas.org, and the first author was Arvind Swanesia-Putra, and he will send you that data if you're interested. So this is what our 7 core labs look like. These are kind of Bland-Altman plots, so we've got EDV, ESV, and we also looked at the volume of the epicardium. And you can see that within each core lab, they do a really consistent job. So 0 here is our mathematically derived consensus, which is kind of like averaging everyone together. And some of the core labs are kind of on that. Some of them are a little bit off one way or the other. But within the core lab, they do a pretty consistent job. And you'd expect that because they train their analysts to get the same answers as everyone else in their lab. So the take-home message is that if you're doing multi-centre studies where you're doing analysis in different centres, you just have to watch out that there will be a bias at every site that is doing contours, even manual contours. Okay, so one way around this might be to get a computer to do it. And this is something which I think is moving very rapidly at the moment, and we do have a lot of action in the machine vision community on automatically contouring a myocardium, and the vendors, the hardware vendors and the software vendors are coming out with more and more automated methods which don't require so much user interaction now. So we ran a challenge recently on some of those methods, and we did this sort of consensus thing again with that. And the nice thing about that is that if you have a new method that comes along and says, well, I think I'm as good as anyone else, we can actually quantitatively assess that by looking at plots of distributions against all the ones that we already have done. And this is the real power of a benchmark data set. So benchmarking and challenges are a really good way to accelerate a field. And this field is going to benefit from having data sets which people have contributed for the purposes of algorithm development. One challenge which has recently finished was run out of the NIH. Here's Andrew Rai, one of the most well-known cardiologists in MRI, explaining how the heart works to the computer vision community. And this was a machine learning challenge ran out of Booz Allen Hamilton, which is actually a management marketing firm, who funded $200,000 in prizes for the best person who could come up with a method for segmenting the left ventricle. And that recently finished. I think that someone did actually pick up that prize, but I haven't actually checked that website. But this is an example of the way that techniques which have originally developed for IBM Watson for playing Jeopardy, or Google did a good job at beating an international master at Go recently, using these sort of deep learning techniques. You can apply them directly to image processing. So I want to talk a little bit about quantification. So once we have images and we have a segmentation, we can actually track things through the cardiac cycle using methods derived from non-rigid registration, and you can, sometimes people call this feature tracking, and there are other names for it from the different vendors. It's basically warping the images to match features. So here is me when I found out that Donald Trump was running for the Republican nomination for the presidency. And this is me when I found out that he'd actually won the Republican nomination for the presidency. And the feature warp here is you can see with the little dark lines, are describing mathematically the change in my emotional state. And the same thing is working on these images here. And we can do that in the short and long axis images and pack that together to give a mathematical representation of the, in this case, the left ventricle. So I want to talk a little bit about how we can use that representation, not only to derive standard measures of LV mass, wall thickness, cavity dimensions, fractional shortening, but also a wide variety of other indices, because now you can interrogate these models at any point which is registered to every heart in our population. So we know that indices like end-systolic volume and sphericity, that's how globular the heart is, are predictive of worse outcomes after myocardial infarction. But we also know through epidemiological studies like MESA, the multi-ethnic study of atherosclerosis, that these shape changes are also present in the asymptomatic population. So it's possible that we can maybe derive scores which are kind of like Z-scores, which we can say, okay, patient X has come in, we've done a 3D stack of MRs, we've calculated the shape, and now we can say how their shape matches with our MESA population, for instance. So that's something which is coming along on the horizon, and I think with the advent of big data and epidemiological studies which use imaging in a Framingham kind of sense, we'll start to see Z-scores appearing for imaging biomarkers. So once we have that, we can design classifiers for particular pathologies and determine how much our shape and motion is matching the the population with that pathology. So the idea there is that we can do this in a shape sense, but also in a motion sense. So we could divide our analysis into the 17-segment American Heart Association method, and we get a curve for every segment in that model. But you don't have to. I think that's was generated from a map of coronaries, which may vary from patient to patient, and also is a very coarse subdivision of the myocardium. So you can do a lot finer resolution indices than just the 17-segment analysis. So once you have a lot of data, you can start to pull out maybe one index, one number, which best characterizes the difference between, say, patients who are remodeling after a myocardial infarction or asymptomatic volunteers. And you can do that using statistical methods which are based on like linear discriminant analysis or machine learning variants of that, which allow you to distinguish between asymptomatic people and myocardial infarction people with a very high level of accuracy, which is just really saying that our indice is a good, it's capturing a lot of the shape changes that happen due to this disease. So for congenital disease, like Mike was talking about in the previous talk, you might want to talk about the right ventricle as well. And that's another whole level of complexity. So there are still controversies on the left ventricle analysis. There are more on the right. The trabeculation is much more difficult to quantify. Also, there's variation in where you put the valves. So the real problem is is where to stop the ventricle at the tricuspid and pulmonary valves, or if it's a tetralogy of Fallot patient, there might not be a pulmonary valve. Where do you actually stop in the outflow tract? And there's a lot of work that needs to be done in standardization, and hopefully open benchmark data sets will help with that. So I just want to switch gears to tagging for a little bit. So we learnt in the first talk that tagging's been used to quantify regional function in a tissue sense rather than a chamber sense. The advantage of tagging is that you are putting markers in the tissue itself, and you are getting an index which is directly related to tissue function, which doesn't have any assumptions due to the geometry or the hypertrophy of the patient. So tagging is a simple preparation pulse sequence, at least in its basic form. There's a 90, which tilts magnetization in the transverse direction. There's a gradient, which wraps the magnetization along in a spatial direction. And there's another 90, which stores that wrapped magnetization back in the longitudinal direction. And there it's available for imaging with whatever sequence you'd like. The nice thing about that is that these tags stick around in the tissue, so they warp. So if you can match the pattern, you can calculate the strain. The way that we do this is through feature tracking, so we're using the same algorithms which we used in the previous slides to track the tags in this case, and the resulting motion of the tags will give rise to strain, in this case circumferential and longitudinal strain, and also radial strain. One recommendation about tagging is that the radial strain that you get from tagging is often quite a bit lower than you would expect. And I think that the reason for that is that the tags are very quietly wide-spaced when you think about the thickness of the myocardium. And the wall thickening that happens in the myocardium is very non-linear from the epicardium to the endocardium. So there's a lot more wall thickening happening at the endocardium than there is at the epicardium. So the value that you get from tagging is completely dependent on where the tags actually happen to fall. Are they more towards the epicardium or more towards the endocardium? You'll get a completely different answer. However, circumferential strain is very robust with tagging, and also the regional variation in circumferential strain and longitudinal shortening strain is very robust with tagging as well. So tagging is probably the most widely used method for strain estimation. But if you're looking at for higher resolution, you really want to think about dents. It's a longer breath hold, it's a more complicated pulse sequence, but it encodes displacement at every pixel. And so you can start to see a much higher resolution variation in strain if you're looking at cases where that is important. This pulse sequence is due to a paper from Fred Epstein and colleagues called CineDents, in which there is an initial tagging preparation sequence, but then another 90 and a decode gradient here, which is reading out the displacement magnetization. So this method differs from tagging in that it encodes displacement in the phase of the signal rather than the magnitude. But you can think of it as a kind of stimulated echo tag, if you like. The nice thing about this method is that the post-processing is a bit easier because you now have a quantitative assessment of displacement at every pixel. So this is the work which was funded by Siemens in our lab, where we wrote a tool to create strain maps from dense images. I know that Fred Epstein at University of Virginia has some very nice open source tools for this. So if you're thinking of doing this in your lab, I would recommend contacting Fred. He has a 3D version and a 2D version and a lot of analysis software as well. So you can start to see that there's a bit of a convergence of strain analysis in this area. So you could use tagging, you could use dents, or you could use untagged SSFP cines and just see if you can track features. One way of figuring out what the artifacts are is by open challenges, so that there was a challenge a couple of years ago comparing motion estimation methods in a variety of imaging modalities, and I think this is a really important way of moving the field forward. One paper which we published recently was looking at why the strain estimation from tagging can be different from the strain estimation from feature tracking. And this figure is in the paper, but the journal in its wisdom decided to leave out the legend. So it made it a little bit difficult to understand. So if you are interested in this figure, you can email me and I'll send you the correct one, which has the explanation. Anyway, the take-home message is that feature tracking works very nicely if you're looking at the strain around a whole slice, like a whole short axis slice or a whole long axis slice. You can calculate the strain from feature tracking. You will get the same answer as you get from tagging. So you don't have to run tagging if you're just interested in that strain, which is like a global strain around the whole contour. However, if you're interested in regional strain, you will get subtle differences if you're using feature tracking from a tagging technique or a dense technique. And the reason is that feature tracking are tracking features which are not really myocardial features, but are features which are between muscle and blood, and that is corrupted by through-plane motions, which will give you artifactual strains. Now, if you're dealing with patients that have really bad regional function, you are going to see that in feature tracking. They'll come up because their barn door regional wall motion abnormalities. But if you're into subtle things, then you'll see an artifact due to feature tracking. So this was a little experiment that we ran just to have a sanity check about what we're tracking when we do feature tracking. So we took our original images and we segmented the myocardium, and then we generated these simulated images. So this simulated image is the same as the original, except that the myocardium has been replaced with an average value. So we've taken all texture information away from the myocardium and we've replaced it with an average value. So we call that the myo mask. This one, we're doing the opposite. So we're keeping the signal due to myocardium, whatever textures that has, and we replace everything outside with a uniform grey level. So we're calling that the X-myo mask. And then this one has both. So we replace all the myocardial pixels with one value, outside with another value, so all we get is left with is information that's to do with contours. If you do that, you'll find that if the whole slice is looked at and you look at the differences between tagging results and feature tracking, you get the same answer regardless. So any of these methods will give you the tagging result over the whole slice, and we think that the reason that is happening is because you're looking at a contour change here. The difference in the length of that contour is giving you the strain. Doesn't matter if you get that from a contour or from some feature tracking, you get the same answer. But you will get different answers regionally in the anterior septum, anterior anterolateral, etc. if you are looking at regional strains, because of the through plane motion that's happening, and trabeculations and other things causing artifacts. Okay. Another thing about strain is that it's different in different directions. So it depends on the direction that you measure it in. If you think about it in 3D, here's the apex, here's the base. Different pieces of myocardium will strain in different ways. So you get circumferential shortening, you'll get longitudinal shortening. You'll also get torsion, which is the relative twist of the apex versus the base during systole. And that's an interesting parameter, particularly mechanically in some patients, and it's received a lot of research down the track. This is the way that I recommend that you quantify torsion with MRI, just using two slices. You can measure the rotation at the base, you can measure the rotation at the apex, you divide by the distance between them, and you also multiply by the radii. Now the reason why you want to multiply by the radii is to get around the effect of different sized hearts. So if you don't do this, then you'll get a different torsion in children and adults and mice and rodents from humans. We know that torsion is very conserved mammalian across the whole mammalian species. So if you use this formula, you should get about the same torsion no matter if you're doing in mice or men. If you're looking through time, you can track strain and strain rate, and often it's the strain rate which will give you information. For instance, with a series of patients with type 2 diabetes versus a series of patients with healthy controls, you will see a slight difference in peak strain, but you'll see a much bigger difference in the relaxation rate of strain. And similarly with aging, you do see more differences with aging in relaxation rate than in the strain itself. There have been a lot of publications over the years on terms of the differences in strain in different cardiomyopathies. One interesting one which is coming out about hypertrophic cardiomyopathy is that you can see differences in torsion in carriers with normal wall thickness before they start to develop symptoms. Just before I end, I'd like to put a little plug in for the next level of stuff that's coming from over the horizons, and that is from systolic function to material function of the myocardium. So can we get material stiffness from MRI? And one method of doing this is elastography. And there's a whole elastography session at this conference. One of my students is presenting a paper on that, showing that it is possibly feasible to extract anisotropic stiffness, so fibre stiffness and cross-fibre stiffness from data which you can get non-invasively using magnetic resonance elastography. Okay, so the take-home messages have been from this talk. Manual contouring is the gold standard, but it does require extensive training in your lab, so at least a few weeks, I would say, to get people on board with the same level that other people are doing. Automated methods, though, are going to standardize this, I hope, in the near future. I would recommend DENTS if you're looking at high-resolution strain, but untagged SSFP can be used for global strain in the whole slice, no problem. All right, thank you very much, students.